Okay, great. Well, thanks for the invitation. It's always cool to be part of eCHT. It's nice to see people from so many different places. I also was going to make a warning that it's raining a lot here, and LA tends to crash in general when it rains, but it seems like things are going okay. So hopefully I won't just, if I disappear, I'll come back and use my hotspot. So this project is joint work with Yang Hu, who's a postdoc at New Mexico State University, and Hood Chatham, who's officially at Cloudflare, but he still will think about math if you send him questions. So I encourage you all to do that if you would like to. So I want to think about vector bundles. This picture that I drew is I'm not actually going to be talking about real vector bundles, so it's just for inspiration. For me, by a vector bundle, I'll mean a homotopy class of maps from some space X, which is usually going to be a finite CW complex, well, actually always in this talk, to the classifying space BUR. So this is a complex vector bundle, since I'm looking at U of UR, complex matrices, complex unitary matrices, and I can consider the map from BUR to the infinite classifying space for stable bundles, BU. And I want to consider in this talk bundles so that the composite, which is the same thing, I might note this composite is the same thing as the K-theory class, the class in reduced K0 of the bundle. I want to consider vector bundles of rank R on my space X, which are stably trivial. So that's this word in the title, of course. I think my notability crashed. Yes, that's what happened. I think that's unrelated to the rain. Just give me 1 second. Hopefully it'll come back. That looks good. So where were we? Right. So if I have a finite CW complex, finite dimensional CW complex, I guess I should say finite dimensional and also needs to have finitely many cells up to homotopy. So there are finitely many vector bundles, equivalence classes of unstable topological vector bundles, which represent a given K-theory class, in particular, which represent the trivial bundle stably. So for example, if we look at a sphere where I guess I should ensure that I'm looking in some appropriate range, then I'm looking at homotopy groups of unitary groups. I mean, I'm always looking at homotopy groups of unitary groups, but if I took 2K to be equal to R, then I wouldn't just be looking at stably trivial bundles when I look at the homotopy groups of unitary groups. So in general, this is something that we don't know. We know a lot of homotopy groups of unitary groups, but not all of them. So the question that we might ask is, how many bundles do I have which are unstably non-equivalent as topological vector bundles, but which stably represent the trivial bundle? So for example, I could ask this for complex projective spaces or for spheres. I'll talk a little bit about even spheres at the end. So the motivation for this project was to study bundles on projective spaces. Projective spaces are something that all of us have thought a lot about. Yang and I both about vector bundles, Hood about orientability problems, and well, therefore also vector bundles. But after sort of proving a lot of things about bundles on projective spaces, we realized we could say some things about bundles on spheres as well. In other words, computing a couple new things about homotopy groups of unitary groups. So hopefully I'll have a chance to say something about that at the end. Okay, so we're trying to find the number of isomorphism classes of stably trivial rank L minus C bundles on CPL. Now, this notation is a little bit confusing because you might want to look at like rank R on CPL, like thinking about choosing a dimension or a rank for your bundle and a dimension for your space. However, it's going to turn out that the way this problem kind of comes together, you want to focus on the co-rank. That kind of is what controls the complexity of the problem. So that's why I've chosen to write this in terms of the dimension and C, which is the dimension minus the rank. or the co-rank, instead of in terms of rank and dimension. So for example, we can compute what this, and I guess I should say, we're looking at bundles on CPL for this part of the talk. So this notation always refers to co-rank C bundles on CPL or rank L minus C bundles. So, oh, I think that there's a mistake in the notation here, which is that, sorry, I'm just going to correct this, but I'm realizing because I have pauses in my slides, it's going to come up on each slide, but that's not such a big problem. So the number of co-rank, oh no, actually what I wrote was correct. Sorry, I just got a little bit confused for a moment with subtraction. Dan, I see you have a question.
Yeah, real quick question. So in this slide, in the previous slide, you've been talking about like the orders of things, like the number of things, so like you're counting elements. Is that because there isn't a group structure around? Normally, like we say things in terms of billion groups or something. Is it because it's not a group, or?
So yeah, on the set in general, if you look at the collection of vector bundles of fixed rank, it's not going to have a group structure. You could look at direct sum, that's going to change the rank. It turns out in some cases there are sort of natural group structures. There's some sort of destabilization of some K-theory addition. For example, if you know that that BU, for example, you have an isomorphism between, or for example, I'll just give you one example. You could look at the map from BSP1 to BSP, and this map has first homotopy group in the fiber of this map. The fiber of the map has the first homotopy group in degree 7. So it's either connective or connected up to something. And this tells you that if you look at rank 1 symplectic bundles on, for example, CP3, they actually have a group structure because of the connectivity of that map. So in some cases, there's sort of an accidental group structure that comes from the fact that you can do your K-theory addition and then destabilize it. But in general, these are not groups. I will show I'll mention a little bit later that there is a group structure that you can put on these things, but it's not obvious what it comes from geometrically. It sort of comes from making something into a stable problem, and then you're looking at pi0 of a spectrum, so there's a group structure, but what is it? So there's not a natural group structure. Okay, so I panicked a little bit with subtraction, but in fact, this is correct. Co-rank L-1 bundles on CPL, what is this? This is the number of isomorphism classes of line bundles. So the rank is 1. So if we're looking at line bundles on complex projective spaces, those are just the bundles O of A for A an integer for all L greater than or equal to 1. So essentially what this tells us is that for any dimension of CPL, there's exactly one stably trivial line bundle, namely the bundle with first Turing class 0 or the trivial bundle. Similarly, if we look at bundles of negative co-rank, meaning a bundle of rank L plus M on CPL for M greater than 0, greater than or equal to 0, in fact, what we see is that these bundles are actually already stable, meaning there's at most one bundle with a given K-theory class. And in particular, there is exactly one bundle of rank greater than the dimension of CPL, which is stably trivial, and that's just the trivial bundle. So these are sort of the uninteresting cases. The interesting regime is therefore when 1 is strictly less than the co-rank, which is strictly less than, strictly less than L. Yes. So if we look at the co-rank 1 bundles on CP3, so this is rank 2 on CP3, it's a result due to Atiyah and Rees that these bundles, there are exactly 2 stably trivial bundles there are exactly 2 stably trivial bundles up to isomorphism of rank 2 on CP3. And they do this using an invariant valued in KO theory. And in fact, their construction also enumerates the number of vector bundles with any prescribed churn data. So choosing a K-theory class for complex projective spaces, choosing a class in reduced K0 is equivalent to choosing churn classes. So you could ask the same enumeration problem for any fixed K-theory class, i.e. any fixed churn data, and they're able to compute the number of isomorphism classes for any fixed K-theory class or any fixed churn data, not just for the 0 data. If we look at the number of co-rank 2 bundles on CP5, i.e. this is the same thing as rank 3 bundles on CP5, complex rank 3 bundles on CP5. The number of bundles here that are stably trivial, I realize I tend to say the number of bundles. A referee has recently pointed out to me that the number of bundles is infinite. So of course I mean the number of isomorphism classes of bundles. This number is equal to 3. And again, for this problem, this was in my thesis, and I defined a invariant valued in TMF localized at the prime 3, which distinguishes the stably equivalent bundles in this case. Something else to say is that this result is also but for any given churn data, not just for the trivial churn data, any given K-theory class. But both of these examples are they rely quite a lot on studying CP3 or CP5 respectively, and doing something that's quite specific to both the given ranks and given dimensions in order to analyze all possible K-theory classes in those fixed those fixed rank and dimension at once. I'm going to come back to KO and TMF a little bit later. If you are sort of someone who knows something about higher real K-theories, these are sort of the first hint, and the reason that I kind of wanted to get higher real K-theories involved in the problem of classifying higher rank bundles on higher dimensional projective spaces. So as opposed to fixing a rank and a dimension and trying to understand that problem in full, trying to understand the number of bundles I guess if you fix your churn data and then also enumerated all bundles with all possible churn data, you've essentially completely classified bundles of a given rank on a given projective space. In this talk, what I want to do is I want to focus on getting partial information about a large number of problems at once. So I'm allowing myself to vary the rank and the dimension. And the key tool here is a theorem due to my collaborator, Yang Hu. He gives an identification for the rank of your bundle between half the dimension of your complex projective space and the dimension of the collection of stably trivial rank R bundles on CPN with stable maps. So I think I have some notes here which might be useful. So this, I guess I didn't actually say what this is. This just means maps of spectra. So just maps in the category of spectra, pi0 of maps in the category of spectra between stunted projective spaces. And I just want to note, because it'll be useful, that I can also think about this as pi-1 of this spectrum where D is the Spanier right head dual. So I just moved things around a little bit here because it's going to be useful to be able to think about this as just a homotopy group of some spectrum. Nothing too fancy going on there. Now, just to say, what is CPNR? There's some different conventions in the literature depending on how far you go back. This is a spectrum which is concentrated in degrees n through r inclusive. So I can think about this as the cofiber of CPR going r-1, sorry, going to CPN in spectra. And it doesn't matter, like an important point is that you don't have a base point here. You've taken pointed suspension spectra, or the base point gets killed if you were to put a plus on both sides. So it doesn't actually matter. Okay, so the proof of this uses Weiss calculus. So Weiss calculus gives you a way to study the functor from inner product spaces over C. So I'm going to call this functor BU dash to pointed topological spaces, which takes an inner product space over C to be U of that inner product space. So what the Weiss calculus gives you is it gives you a tower where you start with BU, that the constant functor, and that's the constant approximation. And then T1, let's call this F for notational purposes. You have this tower like this. And the fact is that when you take the limit of this tower, you're going to get the functor BU back. So this is a tower of functors with nice properties. And the layers of this tower, the fibers of the subsequent stages are going to be infinite loop spaces. And in fact, if you look at L1 of F evaluated on V, where the dimension of V is equal to N, this can be identified with loops infinity, suspension infinity of sigma of CP infinity. Oh, sorry, I don't want my dimension to be N because N is supposed to be the dimension of my space. Let's make this be R. R. So what this tells you is if you're looking at maps from some space X into BU, where this, sorry, if you're looking at, if you're trying to build a map into BUR by mapping iteratively into the stages in this tower, you start with a zero map here, then you go to lift it here. And because you have something that's trivial, you're able to lift here. The choices of map are going to be a torsor for some odd or for a quotient of some odd K-theory group, which for complex projective spaces is zero. So you get an identification of maps from something like CPN with maps into this layer. You get an identification of this side, the set of stably trivial vector bundles, with maps into L1. And that relies also, I guess this is important to say, on some connectivity estimates for this tower. That's where this hypothesis comes from. So this is something we won't really need much about Weiss calculus. I'm just going to kind of take this result and run with it. But I think it's interesting to sort of see where this comes from a little bit, because you can ask, okay, given the things that I'll tell you, can you get more information from this tower? And the answer is definitely yes, just it's going to be a little bit harder than analyzing the information that comes from the first stage in the sort of interpolation from BU back to BUR. Any questions before I move on? Okay, so setting aside the Weiss calculus, we now have this set of stably trivial complex rank R bundles on CPN up to isomorphism. And we know that it's in bijection just as a set with this thing, which is, to come back to Dan's question, this is a group. So now it makes sense to talk about like P torsion in the set of vector bundles, for example, just under the identification of this collection with this group on this side. So in particular, I guess what I should say is that this tells me that the number phi of, I need to be a little bit careful, n minus r is equal to the order of phi minus 1 CP and r smashed with the dual of CP and r. And, you know, we've translated the problem of computing this number into homotopy. So there's lots of tools for computing stable maps. For example, we could just try to do some spectral sequence to compute this in full. And there are other things that we can do, which I'll come to in a minute, to get a complete answer. In particular, if you gave me some like specific n and r, well, either I or one of my collaborators or someone else would probably be able to compute this. However, what I want to focus on in this talk is trying to give some sort of uniform answers for the size of this group. So in particular for C, which is, my convention is always going to be that C is n minus r. Sometimes it's more convenient to write one, sometimes it's more convenient to write the other. So I apologize for some inconsistency. If I fix a small corank, n minus r, I have some very small cell complexes here. The length, the cells are concentrated in degrees. The length of the degrees where these complexes are concentrated is the corank, n minus r. And if I p localize this problem for C small relative to a given prime p, the collection of of maps of spectra from CPNR to its suspension, there are not going to be a lot of maps that can occur because the elements in the stable homotopy groups of spheres that can contribute are all going to be too long. So essentially what I want to say is that the first thing that we can do is just try to work out for small c relative to a given prime, let's compute the size of this group, the size of the p torsion in this group. So for example, for p equals 3 and n equals 5 and c equals 2, we can explicitly work out what CPNR is. It just splits as a sum of a sphere and another sphere. And then this is its suspension here. And we can see that there's exactly one homotopy class. Oh, well, sorry, there's C. Thanks. So C is n minus r. It's the co-rank. And yeah, let me write that again. So it's the co-rank. It's also the length of these complexes. So in this case, we know for rank, for co-rank 2 or rank 3 bundles on CP5, we already know what the answer is. We have three non-isomorphic bundles, which represent the stably trivial bundle, unstable representatives for the stably trivial bundle of rank 3 on CP5. And we can see explicitly what where these bundles come from inside here. We're looking at homotopy classes of maps from CP 5.3 to its suspension. These complexes look like this, and we have exactly an alpha 1 here, which gives us that number 3 because the order of alpha 1, the stable homotopy groups of spheres, is 3. So you can kind of see on this side of the picture how the computations p locally for co-rank small relative to the prime are just going to be quite concrete. So this approach was used by Yang for co-rank 1 and 2 bundles. And in this case, only the primes 2 and 3 can contribute because of the length of the complexes. And Yang was able to prove to completely compute the number of co-rank 1 and 2, i.e. rank L-1 and L-2 bundles on CPL I should add this L greater than or equal to 4. And that's just because you have this condition that you need L over 2 is less than or equal to L minus C is less than or equal to L in order for the isomorphism on the previous page to apply. And this is known as the metastable range. So the stable range is when you're looking at bundles of rank greater than or equal to the dimension of your space. And here you're looking at bundles of rank about half the dimension of the space, at least. So Yang also proves that the number of co-rank 2 bundles is 24 periodic in L. And this is a general phenomenon. You can see, let me go back to the previous slide, you have a James periodicity for stunted projective spaces, which tells you that this number for fixed n minus r is going to be periodic in R with some period that you can compute. What exactly it is, well, there's various formulas, but it's going to grow quite quickly as the co-rank grows. It's kind of hard to write down a closed formula for it, but I can give you the reference if you want. So more precisely, what Hu is able to do is to give all of these numbers just by computing maps between these cell complexes using the periodicity that you have. You can compute this number for any L just by doing 24 cases, of course. So the specific numbers don't matter, but it's just kind of interesting to see that you're getting, quite a lot of different possible multiple powers of 2 and powers of 3 contributing. So was there a question? Oh, I think that's a question that was already asked. Okay, so how about if we look at larger co-rank? That's the starting point for the results that I'm going to tell you about today. I was particularly interested in co-rank p-1 bundles because that I told you about these rank 2 bundles or rank 2 bundles on CP3, which are co-rank 1 bundles on CP3, and this was a 2 local problem. Similarly, if you look at rank 3 bundles on CP5, there's some sort of like a pattern here looking at co-rank p-1 bundles or rank p bundles on CP2 p-2. And in fact, using this identification, we can see that you're going to have p interesting bundles in this case as well. So specifically, you have a p local atom splitting of CP infinity. And if you then cut this off appropriately, you see that you have exactly one term in each atom summand of CP 2p minus 1p. And then if you compute the maps between these, you see that you have exactly one thing that's contributing. There's one sort of alpha 1 in the self maps up to suspension that is contributing. So we get that pi minus 1 of CP 2p minus 1p smashed with its dual is just z mod p, where that's coming from some alpha 1 term. And this tells us, this tells us that the number that we wanted to compute in this case, oh no, I moved my border. This tells us that phi, for some reason my pen isn't working. Phi of the number of stably trivial co-rank p minus 1 bundles on CP2p minus 1 is equal to p times something, where k is not a multiple of p. And you can also kind of see that the only things that can contribute here are smaller primes than p for this factor k. So if you do a similar analysis for the other congruence classes, so this deals with, this is the first case of interest where, well, sorry, let me just say, because of the periodicity that you kind of see, the James periodicity in this case tells you that you only have to compute p congruence classes of rank for co-rank p minus 1. So what we find is that you get a p local splitting where you have now a cofiber of alpha on the bottom. And this kills the thing that gave you the p torsion here, which was a map from the top cell in the source to the bottom cell in the target, the suspension at the bottom cell in the target. So we don't get any p torsion for co-rank p minus 1 on projective spaces of dimension that is not congruent to p minus 1 mod p. Or yeah. So I wrote here something about the p-adic valuation, which is just a rephrasing of the orders of these groups p locally. So you could generalize this argument just working out the explicit cell complexes from the atoms decomposition of CP infinity and the P1 module structure on the mod P cohomology to prove the following. If you're in the metastable range, this condition is always going to be a hypothesis because otherwise we can't compute the map stably. And you fix a co-rank n minus r, which is between 1 and p minus 1, which you might notice this is the degree of alpha 1, then the p-adic valuation, or the p divisibility, that's what we're computing, of the number of co-rank n minus r bundles, or c is n minus r as usual, on CPN is 1 if r falls into one of these equivalence classes, and that's essentially when you're going to have some top piece that can map into the bottom piece, and 0 otherwise. So this tells you that phi of n minus r is p times some number which is not divisible by k, and this tells you, or sorry, p times some number k which is not divisible by p, that p does not divide this number. Okay, so a couple remarks about this. The periodicity comes from James periodicity. That's what multiple of the universal bundle on CPL is stably trivial. And if we fix a co-rank C, something else that you might observe from this is that for all but finitely many prime numbers, we know the p-adic valuation. This is just saying that eventually 2p minus 3 becomes larger than C for all primes p. So the real situation here is that we want to know about primes that are small relative to the co-rank. So the first case that we might look at is when, for example, C is equal to 2p minus 2. That's the first case where the arguments that we get here break down, because we start to see, essentially, if you were to compute a spectral sequence for stable maps from CP13.9 to the suspension of CP13.9, you'd start to see some alpha 2s contributing. So we can actually draw what CP13.9 looks like here. You don't see any alpha 2 attaching maps, but that's kind of the problem. You end up with some extension problems. Oh, I think I wasn't, oops, sorry. I think I slightly messed up my slides there, but no problem. So you basically, what happens is when you look at maps from this complex into the suspension of the bottom piece, there's an alpha 2 extension that can happen. So here we do end up seeing in some homotopy, in some, we're going to see that pi minus 1 of CP13.9 tensor the dual of CP13.9 is going to be Z mod 9. And this kind of indicates the complexity that's going to be starting to arise as the co-rank gets large relative to the prime. And the essential point here is just that the problem doesn't only involve alpha 1s, where I should say, although I think a lot of the audience are homotopy theorists, this is the first element of order P in the stable homotopy groups of spheres. So essentially the reason that we were able to do this analysis in full was because everything only involved alpha 1 up to co-rank 2p minus 3 at the prime P. So the basic idea is that we can just simplify the problem and try to just see what interesting bundles in higher co-rank arise just from alpha 1 attaching maps. And the way that we're going to do this is that we're going to base change to the higher real K-theory EOP minus 1 at the prime P, which is a nice thing that we understand quite well, the height P minus 1 theory at least, which detects alpha 1 but has a relatively small Hurewicz image. So for example, we aren't going to be able to see this sort of alpha 2 problem here. So I won't say very much about higher real K theories. They're constructed from taking fixed points of Morava E theory with respect to a maximal finite subgroup with a Morava stabilizer group. We can essentially say that at p equals 2, the higher real K theory EO1 is essentially KO. At p equals 3, the higher real K theory EO2 is essentially TMF. And the Hurewicz image includes the classes alpha 1 and beta 1, which is kind of useful for knowing what types of vector bundles will show up. There's also a lot more Hurewicz image at p equals 2 and p equals 3, which will be useful later in this talk. We also have a lot of computational techniques, in particular for complex projective spaces. For either CP infinity or CP or a stunted projective space, CPNR, there's a really nice description of the EO module structure, excuse me, of these spaces. So in his thesis, my collaborator Hood set up this theory of algebraic EO modules. And essentially what this means is that you want to study spectra X, so that when you look at the base change to EO modules, this splits as a sum of very nice EO modules. And the assumption that you have a splitting like this essentially tells you, excuse me, that the EO module structure is determined by the module structure over P1, the module structure of mod P cohomology, just as a module over the submodule generated, as a module over the submodule of the Steenrod algebra generated by P1. Excuse me, let me just take a drink. Any questions? Okay, so the idea is we want to study the problem in EO modules. I told you a while back that the p local count of stably trivial rank R bundles on CPN is just the size of this group. Well, sorry, this over the sphere, it is the size of this group. I'm sorry, I had a bit of a cough last week, and occasionally when I talk too much, it kind of comes back. So hopefully just drinking some water will help out with that. So the idea of base changing to EO is that we'd like to instead compute this group. The problem is it's not clear that computing this group tells you anything about this group for general N and R. So what we prove is that for co-rank less than or equal to, oops, sorry, this should actually be strictly less than. There's sort of a plus or minus one issue that is this is still work in progress. So we need to make that a strictly less than sign. For co-rank less than 2p squared minus p plus 2, we can prove that this map is actually surjective, meaning that any EO module map that we build automatically lifts to a map of spectra, and therefore we're detecting interesting bundles by computing EO modules. So as a corollary, for C less than, strictly less than, 2p squared minus p minus 2, and ln C in the metastable range, this number phi LC of stably trivial co-rank C bundles on CPL is some positive multiple of the size of this group. In particular, we can get lower bounds for the number of vector bundles. We can show that bundles exist by computing this. So we can actually compute this group in full. It's essentially a combinatorial exercise, given that you are willing to look at Hood's thesis, because you can the P1 module structure on both of these spaces, and hence also on their smash product, is something that you can just write down very explicitly. Hood tells you how to turn that into a computation of the EO homology. So for example, out of this computation, which is it's quite a complicated computation in full, just in terms of writing down a closed formula, we get a number of concrete results. For example, if you look at the number of co-rank p minus 1 squared bundles on CP p minus 1 squared plus p squared, this is some positive multiple of p to the p minus 1 over 2. You need to make that into an integer, which of course only applies at p equals 2 for all k greater than 0. So there's tons of bundles here. We have no idea what they look like, but we know that they exist because we can compute this group in this example. Any questions about that before I move on?
Do you know anything about injectivity of that map?
It's very far from being injective. In general, you're going to have, we can say that these are heap origin classes in this group and also in this group, but we can't say anything about p divisibility. And in general, you're going to have at least alpha 2 kind of, these classes, they show you that certain classes in the atom spectral sequence for this group are non-zero. And you can see for lots of examples that there are extensions that happen. So the kernel is very large, and in some sense, the thing that I'd really like to be able to say is I'd like to give a surjection onto this group, right? So I know for all but finely many primes, I can compute the p divisibility in full. For primes that are small relative to the co-rank, but not that small, I can get some lower bound. Well, it would be nice to get an upper bound, but that would require different techniques.
Thanks.
So for higher co-rank, maybe let me just go back to this slide. I can still try to compute things about this group. I might not know that the map is surjective, meaning I might not just be able to automatically lift maps here to maps here, but you can still play around, construct maps of EO modules, and try to show in specific examples that they lift to maps of the sphere. So we can still detect non-trivial bundles in this way, just not in kind of a uniform way. So the basic idea is that if you have a class in the homotopy groups of spheres that has non-trivial Hurewicz image in the homotopy groups of EOP -1, you can do this sort of standard thing where you project off onto the top piece, then you map via this element, and of course you need to choose an element in an appropriate degree so that you get a map like this. But given the fact that you can write this down determines which homotopy group it lived in. And then you can include the bottom cell into the suspension of CPNR. So this is some map that exists integrally, and maybe we can show that it's non-zero after tensoring with EO. This is a map of spectra. So the basic idea is that we want to look for situations where, using the description of the EO module structure on CPNR, we can see that the top cell and the bottom cell split after tensoring with EO. Now, this problem is kind of overdetermined because which cells split, which cells in CPNR or EO split, is something that you don't get to choose. For a given co-rank, this is quite a constrained problem. But given that you know what cells are EO split, you can look for elements of the correct order the correct degree in the stable homotopy groups of spheres, and provided that you can find such an element, which is non-zero in the Hurewicz image of EOP -1, and such that you have some split subcomplexes in CPNR, you're just by construction detecting non-zero bundles of order P, or that give you P torsion in the set of stably trivial bundles appropriately interpreted. Now, something to note is that you have a little bit more flexibility than you think here. For example, if you have a split cofiber of alpha-1, you can still do this construction. Just you're going to have to work a little bit harder to show that you get something non-zero by making some argument about the EO splitting and the class in the Hurewicz image. So, for example, there's a result of Belmont and Shimomura. You have these elements which we'll all call theta T in some stable homotopy groups of spheres. And this is an infinite family, which has non-zero Hurewicz image in TMF, therefore also in EO2 at the prime 3. And this gives us infinite families, actually doubly infinite, because you have both the infinitude here, and also you have this periodicity. So this gives us non-trivial rank 3L stably trivial bundles on this space for all L greater than or equal to 0, and also for all T where their theorem applies. I think that's T greater than or equal to 0, but it might be like greater than or equal to 1 or something. No, probably 0 is fine too. So I think I'm fairly short on time. So let me just say that everything that we do works equally well for even cell complexes with the same sort of dimensional constraints. So for example, we realized after doing all of this for complex projective spaces that we could plug in even spheres, and we hoped that we could say something about homotopy groups of unitary groups. It turns out the uniform results that we get from this theorem, if we take a sphere instead of a stunted projective space, they only recover like classical results about homotopy groups of unitary groups. We don't get anything new from the uniform result. But from these sort of constructions, we can show that for example, using this same Belmont-Shimomura results, that for all T greater than 0, for all L greater than or equal to this, we have a non-zero 3 torsion class in this homotopy group of unitary groups. And you get results for odd primes and also for p equals 2 as well from this that give you some new p torsion from this sort of construction, I should say, that gives you new p torsion in homotopy groups of unitary groups. However, this is the only case, well, this and the sort of KO stuff that you can do are the only cases that give you sort of these doubly infinite families that are infinite, both because you have infinite Hurewicz image and because you have this periodicity that you can exploit. Now, I realized that there's one thing that I wanted to say that I didn't get to, which is that we had this James periodicity at the beginning, but you actually get a much better periodicity for this group, and that's because of a result that Hood proved, which is that P times the canonical bundle on CP infinity is EO orientable. So the periodicity here is, in general, the James periodicity will be the periodicity of this group for fixed n minus r will be larger. It'll be periodic at r with period larger than n minus r. So it's growing quite rapidly. That's a pretty poor lower bound, in fact, for how fast it's growing. But here, the co-rank doesn't depend, or sorry, the periodicity doesn't depend on the co-rank. So that's one really nice computational tool here. And that's why in these results, we're getting some periodicity where we just have to add on 3 times L instead of having to add on some, like the James number, essentially. So I think I'm about out of time. So I have some questions here about where you might go with this, but maybe let me let you ask the questions.